Well, another part of the volume of rotation disk method that we employ is sometimes called a washer method. And the way we think about it as a washer is that, well, instead of having a solid disk about an axis of rotation, we think about the way that we would form the volume of a washer, which is really a subtraction process. What we're going to do is that we would take our volume of each disk right here and take the outer radius, and we're going to call that capital R, and subtract away an inner radius volume. We'll use small case letter r for that one. So what essentially is going to happen is we're going to take the volume of the larger unit and subtract away the volume of the smaller unit and get our total volume. And of course, by subtraction, the volume of a washer is going to be pi times r squared h minus pi times small r squared h. And doing the appropriate subtraction right here, or factorization, we can say, well, we've got pi times the difference r squared minus small r squared times h, right? So we just take the difference in the radii square. And that's the way we're going to face this if we're dealing with two functions. If we've got a function f of x and a function g of x, and one is upper and one's lower, just like our area problem, we're going to take the difference between f of x minus g of x squared. So our volume in this case, where we're rotating about the x-axis, is going to be pi times the integral from a to b, where a and b form the limits of our intersecting curves. And we're going to have our upper function, f of x, in this particular example, quantity squared, minus the lower function, g of x, again, quantity squared, dx. And so we're thinking about this in terms of a capital R squared representing our upper function, a lower R squared representing our lower function. Of course, if we're doing this horizontally, in a similar way, we would say that if we have a rightmost function and a leftmost function, we take the rightmost function squared minus the leftmost function squared as our disk radii right here. And so this formulation right here should actually be really, really helpful in keeping that straight. So let's try this with an example. Let's say we're told to find the volume of revolution of the solid bounded by the curves y equals the square root of x and y equals x rotated about the x-axis. So let's first of all determine where these two curves meet. So I have to take the square root of x and set it equal to x and find out where that's true. Of course, squaring both sides gives me x equals x squared. Factoring by setting it to 0, x squared minus x is equal to 0 at x equals 0 and x equals 1. Okay, so the first thing we did was we find our points of intersection, and we're going to use that as our limits of integration. All right, so the next point is that we have to find an upper and a lower function. So let's go ahead and sketch our graph. The graph of y equals the square root of x, of course, looks like a parabola on its side passing through the point 1, 1. And the line y equals x, of course, is a straight line through the origin and the point 1, 1. And so, of course, we want this area between these two curves to be rotated about the x-axis. Okay, a little bit to do there. So, okay, we've got the line y equals x down below as our lower function, and we've got our line, our curve, y equals the square root of x as our upper function. And we're going to do this on the interval from 0 to 1. So the way this is going to look, using our setup, volume equals pi times the integral from a to b, capital R squared, which is our larger upper function, minus lower r squared, which is our lower function right here, dx. In this case, we're using 0 and 1 again as our limits of integration, so 0 to 1. Our upper function is the square root of x, quantity squared, minus our lower function, which is x squared now, times dx. All right, so now it's off to the races right here. Let's go ahead and take this integral of pi from 0 to 1 of x minus x squared dx. Let's see, what do we get right here? Okay, carrying out the integration, we're going to find the volume to be pi times 1/2 x squared minus 1/3 x cubed, evaluated from 1 to 0. Of course, we know how that'll work out as 1/2 times 1 squared minus 1/3 times 1 cubed minus 0. And putting those together, we're going to get pi times 3 minus 2 over 6, which is pi over 6. And so our volume of the shape that's formed right here is going to be pi over 6 cubic units. Very interesting.